This will be a basic discussion of Chapter 2 from Bio 1440. So, basic chemistry. We're going to talk a little bit about the periodic table of elements. Elements are substances like sodium or chloride, or chlorine, I should say, that cannot be broken into another substance by chemical reactions. So sodium, chlorine, hydrogen, these are elements. And you can stick elements together to make molecules, and you can stick different elements together to make compounds, so molecules that consist of more than one type of atom. Oxygen, carbon, hydrogen, and nitrogen are elements that are the most common in the human body. There are 90 naturally occurring elements, but only 12 are really very substantial when in a living thing, and 4 make up 96% of human body weight: carbon, hydrogen, oxygen, and nitrogen. We call these the essential elements. If you were to sell all the elements in your body, you would make a whopping $1 or $2. So nothing terribly rare or expensive in the human body in that case. So matter is composed of atoms, which is the smallest subunit of matter that still has the properties of that element. So gold is an element, and you can have an atom of gold. And once again, an element is a substance that cannot be broken down into another substance by normal chemical means, and they consist of subatomic particles: protons, neutrons, and electrons. So protons are positively charged, neutrons have no charge, and electrons are negatively charged and occur in an orbital around the nucleus. And in reality, they're not in an orbit like a planet. They could be anywhere inside of this cloud, like we see in this image here. We list the elements in the periodic table of elements, and when you look at a element in this list, it'll have the symbol for the element, the atomic number, which is the number of protons, and the mass number, which is the mass of the number of protons and the number of neutrons. So there's, in the case of helium, there's 2 protons. Therefore, we know there's also 2 electrons, because the number of electrons generally equals the number of protons. So protons are positive, electrons are negative, and then neutrons then being neutral. So atomic number is the number of protons. That's how you define what an atom is. The number of protons is usually the same as the number of electrons. So in oxygen, there are 8 protons and 8 electrons. Atomic mass is the sum of the masses of protons and neutrons measured in a unit called daltons. So we have 8 protons, and we have atomic mass of essentially 16 here. So you find the difference between 8 and 16, which is 8, and that tells you how many neutrons there are in oxygen. Electrons have a negative charge and weigh very little. We don't bother putting their mass into the atomic mass. They are located in orbitals around the nucleus most of the time. And if an atom has more electrons than protons, it has a negative charge, and we call that an anion. It's a type of ion, a charged atom. If an atom has more protons than electrons, it will have a positive charge, and we call that a cation. And those electrons are found in energy levels around the nucleus in orbitals of various shapes, which you can learn about in a chemistry course. But one thing I'd like to point out is that if the nucleus of an atom were the size of a golf ball, the first energy level where you'd find those electrons would be a kilometer wide. So an atom is mostly empty space. Another thing I'd like to mention are isotopes. These are elements that possess different numbers of neutrons. So carbon-12, that's a carbon with an atomic mass of 12, and carbon-14 have different numbers of neutrons. And carbon-14 is less stable than carbon-12. They tend to break down, releasing energy. It's a radioactive isotope. And that's the kind of carbon, the ratio of how much carbon 14, for example, you find in a substance can be used to date that substance, because we know how long it takes carbon 14 to break down into, I believe, nitrogen. It breaks down over time, and we know how long it takes half of the atoms in a sample to break down. That's 5,730 years. So you can look at the ratio of carbon to that nitrogen and know how old that sample is. Those electrons that surround these atoms have energy associated with them. Just like a ball at the top of a flight of stairs has more potential energy in it than a ball at the bottom of the stairs, and that ball can release energy by traveling down the stairs. Just like that, an electron in an outer energy level, an energy shell, has more energy in it than an electron at an inner energy shell. But electrons can change energy levels by absorbing energy or losing energy. This will become very important when we talk about energy transfer in the respiration chapter. So hopefully you have a bit of an understanding of how the periodic table works. One thing I want to point out is that the inner energy level of these atoms can hold up to 2 electrons, and then the outer energy levels here can hold generally up to 8 electrons. And if they have fewer than 8 electrons, like this magnesium here that only has 1, that magnesium will be very reactive. But an element like argon that has 8 electrons in its outer energy level will be very unreactive. So if we have 2 atoms like these hydrogens, hydrogen have 1 electron in that energy level here, and this first energy level can hold up to 2. So somewhere in this cloud is that electron. Here's another atom with that electrons in that cloud. They can form what we call a covalent bond, where they share electrons. Each hydrogen is sharing an electron with the other atom to complete that energy shell, and now they're bound together. So a molecule is then a group of atoms held together by chemical bonds. And you can have molecular hydrogen, which is H2, like we saw in that previous slide. H2 is a molecule, it's molecular hydrogen. A compound is a molecule composed of more than one element. For example, H2O is a compound. And the types of bonds that hold these compounds together are covalent bonds, ionic bonds, and we'll also see hydrogen bonds. So here is covalent bonds. Here's what we just saw, hydrogen. Each hydrogen sharing 1 electron with the other hydrogen, completing that inner energy level. Now remember, if there's more than 1 energy level, like in the case of oxygen, oxygen in this case has 6 electrons in its outer energy level. And so in this case, 2 oxygens sharing electrons together, we're sharing pairs of electrons here. We're sharing 2 pairs of electrons per molecule, so we have a double bond. This is a very strong bond. Another thing that comes into play when we're talking about chemical bonds is electronegativity. Electronegativity is a measure of the affinity for electrons that an atom has. For example, hydrogen has a very low electronegativity of around 2. Oxygen has an electronegativity of around 3.5. That means in a bond between hydrogen and oxygen, oxygen will hold on to those electrons more frequently than it will give them to hydrogen. So it has the electrons more often than it shares them with hydrogen. So think of it this way. If 2 atoms, like this case, 2 brothers, a bigger brother and a smaller brother, are sharing a toy, the big brother wants the toy, he's going to get it more often. So he's more electronegative. Think of the toy like an electron. Oxygen, when it's sharing electrons with hydrogen, holds the electrons more frequently than it gives them to hydrogen. That results in a polar covalent bond. Electrons are negative. They spend more time with oxygen. That makes oxygen negative. So if you have oxygen stuck to a hydrogen, the oxygen will have the electrons more frequently. It will be somewhat negative, and then in relation to the oxygen, the hydrogen will be a little bit positive, because those electrons, which I'll write out as E minus, remember electrons are negatively charged, are going to be spending more time close to the oxygen, making it negative. Now if you have two atoms of similar electronegativity, let's go back to this chart. Let's say carbon is bound to hydrogen. They have very similar electronegativity. So you have something like this. You have carbon stuck to a hydrogen here. This bond is a non-polar covalent bond. They share electrons equally, so there's no charge involved. They have electrons about the same amount of time. So the more electronegative an atom, the more it tends to borrow electrons and not share them very easily. Oxygen being very electronegative. So in the case of water, there's a polar covalent bond here between this hydrogen and this oxygen right here. That means the electrons hang out with oxygen a lot. This results in a partial negative charge. They use this sigma signal to represent a partial, sort of a weak negative charge, whereas the hydrogens have a slight positive charge because of that. And this is going to lead to many of the properties that we see in water. For example, we know this oxygen here is negative and this hydrogen is positive. So right here we're going to form a hydrogen bond. They're attracted to each other because of their opposite charges. We're going to see that when you talk more about water in the next chapter. Now, ionic bonds occur in a different situation. These are weaker than covalent bonds. So sometimes an atom will rip an electron off from another atom, and that will change the charge of the two atoms, making one negative and one positive. And then they are attracted to each other because of their opposite charges. So let's look at this example. Here is sodium. Sodium has one electron in its outer energy level. That is unstable. It wants to have up to 8, right? Chlorine has 7 electrons in its outer energy level. It's missing one. So what happens is this electron gets ripped off and sent over here to chlorine. That means the outer energy level in sodium now is 8, and the outer energy level in what is now a chloride ion is 8 as well. But we've lost an electron in sodium, but we have the same number of protons as we had when we started. That leaves us with a cation, a positively charged ion. We have an extra negative electron over on this chloride ion. That makes a negative atom. Now, because of this one being positive and this one being negative, these are attracted to each other, just like a positive side of a magnet is attracted to a negative side of another magnet. This, let me step backwards real quick, this leads to the formation, in this case, of table salt. This is how salt crystals form, through ionic bonds. Like I said, these are weak bonds and they can be broken easily just by dissolving this substance in water. The last type of bond I want to mention, and I already mentioned briefly, are hydrogen bonds. These occur when hydrogen is stuck to something electronegative. So hydrogen has a very weak electronegativity. When it's stuck to something very electronegative, the atoms or the electrons are shared unequally and a charge is formed. Sometimes it's when hydrogen is stuck to oxygen, like in the case of water. So we have plus, plus, and a minus. A lot of times in living things, it's when hydrogen is stuck to a nitrogen, which is also somewhat electronegative. And these bonds are common between water molecules, as we see here. And they're also common in DNA between the two strands of DNA. They're held together with hydrogen bonds. The bases of DNA stick to the opposite base through base pairing, which is held together by hydrogen bonds. So when we're looking at chemicals, these chemicals are dissolved in living things anyway. Chemicals are dissolved in the liquid in our cells and bumping into each other, and chemical reactions take place. And chemical reactions are basically the breaking and forming of new chemical bonds, breaking old bonds, making new bonds. And when we do this, first we start with reactants, that's what you start with, and you produce a product. That's the molecule that you get at the end of the reaction. So for example, in this reaction, 6 water molecules plus 6 carbon dioxide molecules yield glucose and oxygen gas. This is photosynthesis. The opposite reaction is cellular respiration. Oops, respiration. So the products of one reaction can be the reactants in another reaction. So to get these reactions to take place, we change the chemical bonds. We're going to break these covalent bonds and reform them into a new product. For example, hydrogen gas plus oxygen gas yields water. That sounds like a very mild reaction, but in reality, electrons are changing energy levels. I talked about how electrons have energy associated with them depending on what shell they're in around that nucleus. When we break and reform bonds, a lot of energy could be released depending on the reaction. This reaction, for example, results in a big fireball. It's when you light hydrogen on fire, you get this reaction and it produces water. So breaking and reforming chemical bonds is a chemical reaction. And chemical reactions are going to be affected by 3 things. The temperature that those chemicals are in, because these chemicals, like in living things, they're sitting in water. They're dissolved in water and they're bumping into each other. And the more energy in that system, the faster the chemicals are moving, the faster they bump into each other, the faster the reaction takes place. The concentration of reactants and products will affect the rate of the reaction. If there's a bunch of reactants, it will take place quickly. If there's a bunch of products, then they're going to interfere with the reactants bumping into each other and the reaction will slow down. And lastly, and very important to living things, the presence of enzymes, which are organic catalysts. Catalysts allow reactions to take place at lower temperatures. They speed up the rate of reactions like at body temperature, allowing for reactions to take place at the temperatures that life exists at. So that's a summary of basic chemistry, basically chapter 2 of your book. Chapter 3 you will have learned about in lecture, and there's also some videos for other chapters located on my website. So good luck studying, and I will see you soon in class.